Chris is also a friend. We 23 years ago when I was still a young postdoc. We've been working together. So I'm very happy to have Chris coming here. He's a fantastic speaker. For those of you who are not here on Tuesday, I'm sure you enjoy this talk. Now, I don't want to take away too much time. Just to mention that Chris is a fantastic mathematician, obviously, but he also does all kinds of outreach and speaking to school kids. We just learned he's also on diversity committee, very passionate about women in mathematics, and so on. So he's going to talk about climate, good, bad, and ugly. Welcome.
Thank you for welcoming. It's of course classic that I give a talk on climate change on a really wet night. So thank you all of you for making all the effort to come here. So it's a great pleasure to be here. I love coming to Toronto, I love coming to the fields, I love coming to Canada. But my home institution is the University of Bath, where I run a program in industrial math. But just in my terms of credentials for this evening, I work very, very closely with the UK Met Office, which is actually quite close to Bath. It's about an hour away. And these are two climate networks which I am closely involved with, where we try to introduce mathematicians to climate scientists and look at the link between them. So climate is obviously an extremely important thing for us to worry about. And one of the things I like about working in climate research is most mathematics you do in your office, you never meet people. But when you do climate research, you meet lots of people. And you meet people from all sorts of backgrounds and interests. And basically, climate change is a controversial topic, unlike much of maths. It's an important topic, like all of maths. But most importantly, for me, it's an area where the mathematics I do brings me into close contact with scientists and even policymakers. So one of the reasons I can't be in Canada for as long as I want is I'm going to be going to Parliament in the UK on the 26th of November to talk to MPs about this very topic. I'm not going to be very preachy today. I'm not going to talk about the rights and wrongs of climate change or what we should all be doing and stuff. What I want to do is talk about the mathematical modelling of climate change and how that can help us make informed decisions, hopefully different from sort of political hype, where we can actually use factual reasoning to work out what we should be doing. So climate modelling is basically hard. It's hard, it's an uncertain problem, there's lots of uncertainty in it, and one of the problems about it is we don't have a terribly large amount of data. And government, the people I'll be talking to in November, or later on in this month, have to do an incredibly hard job, which is to kind of predict into the future, to think, what's the world going to be like in 20 years' time, or stuff like that. And to do that, they use what are called Earth System Models, ESMs. And here is an example of an Earth System Model, or an Integrated Assessment Model, as it's called. And on one side, we have climate models, which I'm going to tell you about today, which are the easy bit. They're the bit which try to forecast the climate into the future. Okay. When I say easy, I'm talking relative terms here. They link up to other things which are slightly less easy, where we look at the impact of climate on things like the ecosystem, on agriculture, on transport and the economy. And then here's the really hard bit, where we try to work out how it's going to impact on human beings and how we live our lives. So this is an Earth system model, and it's ghastly. And the question is it worth it? Yes, it's worth it, because it's better than being completely random. But I'm going to tell you about this bit over here, which is how we model climate into the future, and also how we look at past climate and how we use that to inform our decisions as well. So this is a little bit of bladed advertising. This is a Met Office slide showing the various types of model that they use. So these are different, basically, codes that are used by different operations that they do. Some are these Earth system models over here, and some are basically different types of climate model. And some models try to forecast 100 years into the future. Some just try to tell you what the weather's going to be tomorrow. Some work on quite small length scales, and some work on large length scales. So this is a kind of array of different things that we use. So if I want to forecast tomorrow's weather, and by the way, despite rumours to the contrary, we're quite good at doing that, okay, I will just about believe tomorrow's weather forecast. In the Met Office, they use mostly a thing called MOGREPS for that, which can forecast very reliably over 48 hours at a length scale of about 1.5 kilometres. But if you want to forecast the climate, you can't do that. So if you want to go 100 years into the future, this is the sort of stuff you have. The ones I kind of rely on over here, where you're trying to do really complicated climate chemistry, are things like this. HADGEM. HAD stands for Hadley Centre, which is the main UK climate centre. I know for a fact that what's going on in Canada is pretty similar, because the Canadian Met Office uses pretty well the same codes as the UK does. It's part of a big collaborative programme, and I know that there's been a lot of scientific interplay between the two groups. So this is kind of the kind of spread of things which is going on. So why am I interested in climate? Well, basically, despite rumours to the contrary given by certain US presidents, the indications are that climate is changing. Okay. And I'll try and give you some of what I call the facts. You may disagree with me, but this is the evidence that is presented by the IPCC, that's the International Panel for Climate Change, which had a recent, they kind of reported about a month ago or thereabouts about what's going on. So here are indicators that the climate is changing. Oops, wrong one. The first one is temperature. So, until recently, climate change was called global warming. Okay? And the primary indicator that things are happening is that the world is getting warmer. Now, how do we know this? There are different types of measurements that you can use about temperature. The Met Office in the UK was founded 150 years ago as the first weather centre in the world to take detailed measurements. So we have detailed measurements of weather in terms of temperature, rainfall and all that from about 150 years ago, measured directly. So that's from a thermometer or something like that. If you want to go further in the past, we use things called proxies. So an example of a proxy is the amount of isotopes of oxygen, different types of oxygen in the atmosphere, and the proportions of the isotopes is directly proportional to the temperature, and the way that you record them is typically in things like ice cores and stuff like that. Another proxy for temperature is tree rings. Another proxy for temperature is historical records, for example, from French wine growers about how their wine growing seasons work. So you've got a lot of kind of measurements. Tree rings and ice cores are really good. And these are temperatures going back about 2,000 years ago. The different colours refer to different proxy measurements, but they all basically say the same thing, that about 2,000 years ago things were kind of cold, and then they warmed up, and that warming up led to the Middle Ages. Then things cooled down quite a lot. That was the Little Ice Age, so there's portraits by Bruegel and stuff, with people skating on the Thames or Holland and stuff like that. But then things have steadily gone up and up and up. In fact, this is a picture that stopped at 2000, but they're carrying on and on and on. the temperatures have simply gone up and up and up. And the last decade has been easily the warmest decade since modern records began. That's records are going back 150 years. So it is getting warmer. Here's a kind of a look at the actual measured data, looking at the mean. So what you see here is something which goes up and down. You do get variations in temperature. The primary causes of these are things like El Nino, where you get temperature variations roughly every 4 years, largely due to ocean currents in the Pacific. You also get things like volcanic eruptions, which cause temperatures to change. But broadly speaking, and the red curve is the averaging low-pass filter, you can see that the temperatures are steadily going on and on and on, going up and up and up, and we have a sort of variation, a random variation on top of that. So yeah, there's 1980, and it's pretty well been steadily upwards since then. So there we are. It's very hard to argue against that. The evidence is that things are getting warmer. Another clear piece of evidence that things are changing in the climate is occurring, and it's very relevant to you guys, is Arctic ice loss. So the amount of ice in the Arctic is definitely going down. It goes down by an amount essentially the size of Scotland every year. Okay. So it's going down a lot. Why is this going to affect you guys? Well, you might well see a large amount of sea traffic going very close to your borders, and my understanding is as ice freezes and this land becomes more habitable, the Americans and Russians start sniffing around about Canadian territory. Okay, so there are political reasons why Canada, more than any other country, should be worried about the ice loss. We'll come back a bit later on to look at some of the evidence related to ice loss. But basically, you can measure it. That's the 1980 amount, 1998, 2012. The Arctic is definitely going down. What's kind of, there's NASA's conclusion. Not only is it reducing in area, it's becoming thinner as well. They take measurements by radar of the depth of the ice. What's interesting is in New Zealand, things are slightly different. They worry about the Antarctic in New Zealand, and the sea ice around Antarctica is at the moment increasing. But that isn't terribly good news. It's increasing because the land ice sitting on Antarctica is decreasing, and it's turning into sea ice. So the total amount of ice in the world is going down, and that clearly is an indicator that things are warming up. There was an article just today from the IPCC where they are realizing that far more energy is being soaked up by the oceans than their original models predicted, and that's a contributing factor to the sea ice that we're losing. Okay. Another one, sorry, this is a somewhat UK thing, but we're seeing more extreme events occurring. Now, one of the commonly held misunderstandings about warming is that the IPCC have asked, or the Paris Protocol has said, we want to keep our temperatures below 1.5 degrees centigrade over the next few decades. And you might think, oh, what's 1.5 degrees C? That's nothing. You know, we get a far bigger variation than that during the day. But if you change the mean of a distribution by that amount, it significantly increases the probability of having extreme events. So if the world increases on average by 1.5 degrees, it means you're much more likely to get higher temperatures in extreme events. This is a consequence of statistics. And one of the effects of that is you get more rainfall. And in the UK, certainly, we've been getting far more and far larger rainstorms in recent years. I had a wonderful example of this.
Sorry,
yeah.
I'm confused. So you're saying if you increase the mean without increasing the variance?
If you keep the variance the same and increase the mean, because the tails basically go up a lot. It's just the effect of shifting exponential upwards.
I see. But is this really, I mean, I would have thought that what was actually more significant was the variance was increasing.
Both are important, but even shifting the mean. I'll tell you a good story. One of the things I'm particularly interested in is the impact of climate change on various things like the transport system. And we organised a seminar at Bath, or a workshop on Bath, on the impact of extreme events on the transport system. And unfortunately, we had to cancel the seminar because of the effect of extreme weather events on the transport system meant that nobody could get to us. So I enjoyed sending an email out explaining that one. We're definitely getting more storms. I presume you're getting more storms than we can. Another effect, and again this is absolutely measurable, undeniable effect, that sea level is going up. Now you can measure sea level in one of two ways. One is by simple measurements of sea level by tide tables, tide gauges, and the other is by satellites. And this is sea level rise over the last 20 years or so, and it is absolutely going up. Sea level has gone up by 100 millimetres in that last 20 years, which is quite a lot. Now it's going up for two reasons. One is because as the sea gets warmer, it expands, and therefore it goes up. And secondly, as land ice melts and goes into the sea, so the amount of fresh water in the sea increases, and therefore sea rise goes up. So the primary effect at the moment is warming, because most of the ice that's been melting has been sea ice, and that doesn't change things. But if the Greenland ice sheet were to melt, sea rise would go up a great deal. This would be the consequence. If Greenland was to melt, and most of Antarctica was to melt, then sea level will go up an enormous amount, 170 metres. You guys are more or less okay, but the UK isn't. So we'll have to come and live here. So that's the effect. And of course, other areas, large amounts of Europe, all as part of the US, would get cold. One of the huge effects of sea level rise is that the majority of the really big cities in the world are actually closer to the sea, New York and places like that, and therefore they're very vulnerable to sea level rise.
Sorry, so what I see is that, for example, the Atlantic coast of North America has much more coverage than the Pacific coast. Is that because the gradient is steeper on the Pacific coast? Or?
I'd always assumed that was just the height of it and so on. I think it's just that. Okay, and here's another kind of cause and effect sort of thing, which is the amount of carbon dioxide. So there's an observatory on the top of Hawaii, the Mauna Loa Observatory, which monitors carbon dioxide. In pre-industrial levels, the amount of carbon dioxide in the atmosphere was around about 200, 250 parts per million. We're now looking at over 400 parts per million. So carbon dioxide, it goes up and down during the year, but really well monotone increasing. It's going up. And later on in this talk, I'll show you how mathematical models link carbon dioxide increase to temperature increase. There's a little bit of controversy here, and this is one of the issues in climate discussions, as to does carbon dioxide go up because it's getting hotter, or does it get hotter because the carbon dioxide is going up? Mathematical models indicate the latter rather than the former. But without doubt, it's going up. That's the amount of carbon dioxide in the last 1,000 years, so that's the year 1000. This is the current day. Again, we can measure that by, there's lots of ways of measuring carbon dioxide. Looking at bubbles in ice is a good way of doing it. And so it wobbled around sort of the 200, 250 mark up to about here. At this point, people thought, hey, if you burn coal, we can do stuff. So they started burning a lot of coal, and carbon dioxide has gone up very rapidly. Now, one of the issues with climate change, this is something which mathematical models really have to start to get our head around, is this. The amount of carbon dioxide in the atmosphere has gone up and down over the course of millennia. I mean, there's no doubt about that. And the Earth has adjusted to that. But what we're seeing here is almost a doubling, well, certainly a very large rise in carbon dioxide over, from the point of view of the Earth's history, an instant of time. It's not so much the fact it's going up, it's that it's going up fast. And that's something which models have to kind of try and adjust to. Is the speed that it's going up something which is going to cause a problem? If it was going up slowly, we might imagine the world would stabilise. But this is the problem. It's going up incredibly fast. It's going up much, much faster than ever it has in the past. Okay. And here's the kind of graph looking at temperature rise against CO2. And just from an eyeball on that, there's a correlation between the two. Okay. And as I say, we'll come back later on in this talk to why there's that correlation. Okay, not everyone agrees with this. The Daily Express, if you ever read it, is famously opposed to climate change. It's also famously in favour of Brexit. Okay. This is Simon Cowell, you may recognise. Climate change essentially is controversial. 90% of scientists in a recent survey agreed that CO2 was responsible, but not everyone agrees. So the data, this issue isn't cut and dried. There is a lot of uncertainty in the whole business. And some people think it's all a conspiracy. Recently, well not so recently, a few years ago, someone hacked into the website of one of the big climate centres in the UK, in Norwich, and found some emails where certain of the scientists and mathematicians were talking about the tricks that they were using to do their calculations, and they saw the word trick and realised it must be all wrong, not realising that Jean and I would use the word trick all the time to talk about what we do. So, whilst there's a lot of evidence of climate change, it's certainly not completely conclusive, and that's why there's all this big debate. And it is hard, and here's some reasons why it's hard. So there's a lovely quote from Niels Bohr. I believe this was a similar quote from Yogi Berra, the baseball player, which is very hard to predict anything, particularly about the future. And here are some reasons why climate change is difficult to really nail down. One is that the data has a large amount of statistical variation in it, and we'll have a look at that in a minute. And some of the data that we really want, we haven't got. So it's very hard to get data of what's happening in the future. We've only got one Earth, so we've only got one timeline. We can't say what would happen if we tried something else and run it forward. And if you want to do measurements in the Antarctic is not the easiest place to do measurements. Another reason for the uncertainty is that the systems that we deal with in climate change models are very non-linear, and they have chaotic responses. I'll talk a bit more about that as we go on. Another is that the climate is very, very complex. Current climate models have easily 1 billion degrees of freedom, if not more. And one thing that worries me deeply as a computational scientist is that not only do you have 1 billion degrees of freedom, the codes that we use to do climate change with have probably got millions of lines of code. What if one of those is wrong? You know? And that's a very reasonable question. Anyone that's written code knows how hard it is to write good code. So we have to be very careful how we test these models. And a really difficult one as well is determining what's the effect of human variation and what's the effect of natural variation. But all of these are things that you can address in the sort of mathematical models that we use to try to understand what's going on in climate change. So, just to show you how complicated this is, I apologise for the simplicity of the next few slides, but this is something I like doing with school kids so that we can kind of get some essence of what the issue is. And I hope you don't mind me treating you like not like school kids, but showing you kind of the issues in that way. NASA has an outfit called the National Snow and Ice Data Centre, and they have satellites that buzz around, and one of the things that they can measure is the area of sea ice over the Arctic. And they've been doing this since about 1979. So that's a very clear statistic that you can measure. You just look at the amount from the satellite. There's kind of no real controversy about the measurements. And when they started in 1979 and measured the amount of sea ice, they got this for the first 4 years. So let us imagine we are a government looking at that data. I think any reasonable interpretation of that data is that the sea ice is possibly going up. Okay. So that's a reasonable conclusion from that data. Let's take it a bit more. Let's take what happens next. I apologise for the slight simplicity of this. If you take the same thing over 10 years, this is 10 years worth of the same data, of the same satellites. We start here, we go up, there's the bit we go up, and then it dramatically drops, and then went up and goes on. And I don't think anyone would reasonably be able to conclude either that it was going up or going down. The statistical test would say that it was constant plus some variation on the top. So my advice to the government over 10 years in that would be steady as she goes. Okay, things are staying pretty well the same. If you do it over even longer, this is over 18 years, again, that's where we got to another big drop, but then come again. And again, well, it's really hard, even over that length of time, to see what's going on. And again, if we try to calibrate a model on that, our conclusions would be difficult. But that's what's happened up to more recent years. So we've had all this, but now if we actually carry on, we have to wait for quite a while. And this is why we get worried. This is a graph up to about 2010, but actually, if you continue it, it continues to go down. And this shows a difficulty in how we deal with data. You have to wait for a while in stuff like climate to see what's really going on. Here's the worrying thing. We can fix a straight line for that data, and then we can use that to predict the future, and the future tells us that all the ice is gone by the end of the century. If you talk to some of my colleagues in the Met Office, they would say with their models the ice is gone in 30 years. So that is considerable cause for concern. And that's, again, the IPCC saying that this energy going into the sea, rather than other ways, gives us even more cause for concern. So, oh yeah, that's just taking it on to 2017, showing that that trend really has been continuing onwards and going down. There is absolutely no doubt from that evidence that the amount of sea ice is going down. Next objection that I pointed out was this thing due to chaos theory. Now, if I was giving this talk in England, I would have a demonstration at this point. Unfortunately, my demonstration is too dangerous to take on an aeroplane where they think of it as a weapon, so I'm going to have to tell you what it is. But if you go onto YouTube and type double pendulum, there's a thing called double pendulum, which is basically like a pendulum, but one pendulum connected to the other, like a leg, okay, which is a mechanical system with 4 degrees of freedom, 2 angles and 2 velocities. This obeys Newton's laws. We can write down the equations exactly. But if you set it off, the motion is what we call chaotic. Some of you may have, or many, probably most of you will have heard of the butterfly effect. And the butterfly effect says that certain systems which are defined by perfectly good laws have the property that if you change the initial conditions by a small amount, traditionally a butterfly flattening its wings, that will cause huge amounts of change in the future. And the butterfly effect is there in the systems that we look at. This is why, despite what anyone tells you, we cannot forecast the weather reliably more than about a week in advance. In a week's time, the uncertainty that we make in our measurements of the current atmospheric state accumulate and accumulate and accumulate to make the weather completely uncertain a week into the future. We can make rough estimates, but nothing particularly certain. And that's a fact of life. Climate systems do behave in this sort of way. And what this means is, I cannot tell you in 10 years' time exactly what will be happening on the 1st of November. Yes?
You mentioned a model for the short-time forecasting
Yeah.
and another one for long-term forecasting.
That's what I was going to discuss, yeah. So the Met Office or the Canadian forecast will give you a pretty accurate answer of what's going to happen in a day. Okay? As you increase the number of days, the areas get bigger and bigger. Maybe a week's a bit of an certainly after 10 days, the areas get too big to be anything meaningful. So I cannot forecast the weather. I cannot tell you what's going to happen on the November the 1st, 2028. Okay? Hopefully the Fields Institute will still be here. Hopefully most possible will still be here, but I can't tell you what the weather is. But climate, we can say. Climate is kind of an average. It's what we expect to have. Climate is what we expect to have, weather is what we actually get. So you could probably say that it will be on average warmer or on average cooler. And that's what climate models are trying to do. Okay? They're trying to give you more average information. And that gets around the chaotic problem where, although the butterfly may change what the weather does, the butterfly won't change the overall trend of the weather. And that's a real thing. This pendulum of mine, if you let it swing for long enough, will stop swinging. That will happen. Can I recommend that you go onto YouTube and type double pendulum, and you'll see one in action. You may even see me. Just a little description of what I am here today. I am a thing wonderfully called Gresham Professor of Geometry. The Gresham Professor of Geometry. I give a lecture once a month in London on some subject which I find interesting. And I gave a lecture last month it was called Can Maths Predict the Future? And it was a lecture on chaos theory. If you type Chris Clark, Can Maths Predict the Future? You will see me talking about the double pendulum and swinging one, so you can get the full works. Another issue I said that climate modelling is controversial is this issue of what is happening due to the effects of human beings and what is just natural variation. Okay, is what we're seeing just the Earth doing what the Earth does? So to help answer that question, I want to sort of take you back into the past. Again, you might say, well, how do we know what's going on in the past? And the answer is, typically you drill down into the ice in places like Greenland or Antarctica, and you look in the ice cores at the amount of carbon dioxide, the amount of oxygen isotopes, and so on, and also look at the salinity of the ice. And from that, you can make very good estimates of what the temperature was, and how much ice there was, and how much carbon dioxide there was.
So much harder to do that with all the ice is melted, I suppose.
Well, you cross calibrate to work out where it is, but you can go back certainly a few million years. Quite happily. And this is what you get. And this is one of my favourite graphs. This is a graph I spend a lot of my life trying to understand. Okay. Let me explain what's going on here. This is time, so that's the present day, and that's about 500,000 years ago. Okay. These are two different ice cores taken from different places, and these two estimates of the temperature of the Earth at those two different places. The bottom one is an estimate of the total ice volume covering the Earth. It's plotted upside down for good reasons, so that's low and that's high there. And what's really fascinating is you get this strong, almost clockwork regularity to the temperature. It basically goes up quickly, it goes down slowly. It goes up quickly, down slowly. Up quickly, wiggles a bit, but down slowly, up quickly, down slowly, up and so on. You get this repeated process of relatively quick warming. When I say relatively quick, we're not talking about decades here, we're talking a few thousand years, okay? Or more than a few, but it goes up, you know, in about 4,000 or 5,000 years, and then it cools down, and this, what's called glacial cycle, takes about 100,000 years. Okay. And these are the ice ages. If you look on here, the warming corresponds to a rapid decrease in the amount of ice, and then we get an increase in the amount of ice, and then we get to some sort of minimum, and then it goes up and down, up and down. So this here was the most recent ice age. Okay, that's where our, within, not quite within recorded history in terms of writing, but certainly recorded history in terms of cave paintings and so on. We can see what was going on there. And then this is called the Younger Dryas. This was a rapid rise in temperature about 10,000 years ago. And we enter what's called the Holocene, which is the current time where things are sort of wobbling around it. So this is a clockwork thing. This is how the ice ages have been for the last 500,000 years. And one of the things I'm fascinated about and do a lot of research on is, in fact, why you get all this. But there's this extreme regularity of warming and then slow cooling. So if nature was left to itself, we would expect the Earth to be cooling down. We kind of warmed up 10,000 years ago, started the modern era. We should now be cooling down slowly. That's what the natural cycle would be. Except we're not. This is an interesting picture. I do apologise, this picture goes backwards. I took this out of a paper where some climate papers do time increasing from left to right and some from right to left. It's annoying like anything. But this is going backwards 2.5 million years ago. And these are the 100,000 year cycles up to about 500,000 years ago. And then something happened 500,000 years ago. We get to think of the mid-Pleistocene transition. You get a very different type of behaviour. And again, this is subject to a lot of research and something I'm extremely interested in from the point of view of dynamical systems. Okay. But I say that the essential point is that at the moment the climate seems to be in a 100,000 year cycle and we should be cooling down, okay, if nature was left to itself. And yes, we get this close correlation between carbon dioxide and temperature, again, over the last period, there's this close correlation. Why do we get this variation? Well, there's many different theories out there, but one thing that's clearly important is the fact that the sun is changing, not the sun itself is changing, but the Earth wobbles on its axis, and as it wobbles on its axis, so the amount of radiation from the sun that hits us changes, and these are called the Kovitch cycles. In the 1970s, these were thought to be completely the answer to the ice ages. We feel that it's a bit more complicated now, but the ice ages are definitely related to the Kovitch cycles, which gives us an understanding of what's happening. So that's what happened in the past. And what climate models try to do, before they do anything else, is predict what happened in the past, which doesn't sound as complex as it is. What you do is you take these models, you initialize them with some aspects of the climate in the past and run them forward to see whether they at least agree with what happened next. That's how you test things. So the question is, what happens next? And this is where the climate modeling comes in. So climate centers basically try to work out what happens next using mathematical model. And the basic approach isn't rocket science, it's good, solid, established science. You take the laws of atmospheric motion or ocean current circulation, which go back to Newton and are well understood, and you combine these with the laws of heat transfer and thermodynamics, which are due to Kelvin over here, and you kind of add in extra effects, but not a lot of extra effects. And it's those two. In fact, these are exactly the same as we use for weather forecasting. One test, or one sort of way that we are confident that the climate models cannot be too wrong is that climate models are based on weather forecasting models. And weather forecasting models are tested every day when you look at the weather forecast. So we turn these into partial differential equations. I'll show you those in a minute. And these are the sort of supercomputers that you then use to solve them. Okay. Small joke, except it's not funny. So supercomputers to look at the climate are solving trillions of equations all the time. To do this, they require a lot of power. They need industrial strength power. The typical supercomputer needs about 5 megawatts of power to run. That's a lot of power. These things contribute to global warming. And mathematicians try to work out how to use less power so that they don't heat the world up. So that's the computer at the Having Centre. So these, let's sort of have a look at this. These are the sort of things that you try to understand: climate, air pressure, velocity, temperatures, densities. You do this for the oceans and the atmosphere. You include the effects of ice, you include salt and all sorts of other things, all affected by solar radiation, rotation of the Earth's gravity, and this lot, and then there's the big question mark, ... human activity. Okay. I haven't got that in because you can't easily put that as a mathematical thing. You have to essentially guess what humans are going to do in the next 20 years. Some humans are easier to guess than others. Okay, to do that, and this is the differential equations which are used to forecast your weather. So these are, I unashamedly put these up in a public lecture, okay, because these are great. These are the equations that we use every day to solve the weather, and broadly speaking, they go back to the great mathematician Leonard. Wonderful things. What we do with these, this is motion of the air, density of the air, temperature of the air, water moisture, pressure of the air, and to build in climate, you add in extra things like carbon dioxide and stuff like that. And this shows you how climate models have increased in sophistication over the last 30 years or so, or 40 years. So in the 1970s, you could do sun and rain and a bit of carbon dioxide, and now they bring in all of this. And here I get to the title of my talk: Good, Bad and Ugly. Okay. What makes a good climate model? It's one where we try to account for the system in a way that we can test and in a way which we can validate. A bad climate model is one where you have so much uncertainty that you can't test or validate it on what's going on. And an ugly climate model, the sort of things they use in the climate centres, where they're probably okay, but I don't know really why. So those are the range of models. And this is a publicity slide from the Hadley Centre showing how they are evolving their models in detail with all these sort of things going on. So all of these sort of circles here would represent an entire research group moving away, trying to build all this sort of complexity into the models that we do. So let me just sort of go back and sort of think a bit more about these models. This is what we are using to inform government policy. This is what we are using to think about how we might modify our lifestyle over the next few years. Things like reducing carbon dioxide, having fewer animals producing methane and stuff like that. And I think it's really important that we understand when we use them, firstly, that they are approximations, that there is uncertainty associated with them, and the second, that we test them to death before we actually release them into the public use, as it were. And with all those millions of lines of code, we have to be very careful. And the two ways that these are tested are, firstly, they are based on, as I say, weather models, where we know we have to test the weather every day to make sure it's right. And also they're tested through a process of what's called hindcasting. So a classic test would be, we go back to the year 1900, where we have pretty good data in 1900. We say, right, let's use that to initialize my model, we'll run it forward. And if it reproduces what's going on, then hopefully it's working right. And that's what they do. And they can also do an interesting what-if experiment. They can say, we'll run the model forward with the measured levels of CO2, which are due to human activity, and we can run it forward, keeping the CO2 constant at a 1900 level. And if you run it forward, keeping it constant, you do not get the temperatures that we see. And if you run it forward, putting in human activity, you do. So that acts not only as a test of the climate model, but also as a validation of the hypothesis that what we're seeing is due to human activity. So that's the process of hindcasting. Although it worries me a bit, it's very hard to predict the future, but it's very easy to predict the past if you know what the past did. So we have to be careful not to fool ourselves into a false sense of security for doing that. Okay. So one of the ways that we can also independently sort of test and, I suppose, validate these models is, rather than using these big, ugly, complex, horrible things, we can use what I call good models, which are simpler things, where we have the basic physics in there that we can validate really carefully and actually do some mathematics on, so that we can compare what we think is going on with what's being spewed out by the computer. And there's a whole what we call hierarchy of models that do this, varying from very straightforward ones all the way up to these global climate models. I can't possibly go through all of these. Suffice to say that, as I say, there's different types, but the simplest are what we call energy balance models. And I want to just take you through those because I think they're remarkably useful and pretty predictive. So an energy balance model says, I imagine the Earth to be a single thing, okay? Forget the fact that we've got lots of variation over the Earth. We'll just imagine it to be a single thing which gets hot. And you get energy coming into the Earth from the sun, and you have energy going out from the Earth into space. That's an energy balance model. Energy in equals energy out. So energy, this is a nice picture of the sort of energy that comes in. The key number is this, which is 342. That is the average amount of energy in watts per square metre hitting the Earth. If you have solar panels on your roof, that's an important number. Okay, 342 watts per square metre. So square metre on your roof, on average, that's the amount of the energy you will be able to gather if your solar cells were efficient. And then that's radiated out into space. So heat from the sun in, that's our 342, and that we'll call that S. We'll imagine then the whole of the Earth heats up to temperature T, and that goes out into space. Okay, so if we simplify things down to that level, we can be pretty clear about what the physics should be. So heat comes in from the sun. A certain proportion of that is radiated into space. We call that A times S. That's due to what's called the albedo of the Earth. The Earth reflects a certain amount out. So the amount that actually comes in is 1 minus A times S. The Earth then radiates away, and the model that's reasonable for that is to assume that the Earth acts as a black body, and that the amount of radiation is proportional to its absolute temperature to the fourth power. And there's a constant proportionality called E, which tells us how much energy is released into space. So for the Earth, E is sort of around 0.5 or something. I'll give you the right number in a second. For the Moon, E is about 1. Okay, the Moon radiates everything in space. A lot of the Earth's radiation coming out as infrared is absorbed by clouds and reflected back to Earth. And then you just balance the two. Okay, that's it. So we know what S is. We can measure A, you can measure E. Sigma here is constant, and that is an equation which we can therefore solve. Unlike most kind of models which are impossible to solve, we can solve this one. This chap here is Boltzmann, who's looking at his constants over here. These are the, E is 0.6. These are the currently accepted values for this, and there's our equation, and we just solve it. And there's our simplest equation, the formula there is for climate. Okay, it is simple, but it is predictive. It is predictive. So let's have a look at its predictions. This is Arrhenius, who is well known to everyone who works in heat transfer, who actually derived this equation back in the 19th century. Two very simple predictions from this. As the albedo decreases, the temperature increases. So as A decreases, the temperature increases. As E decreases, then T increases. So E tells you how much energy is released into space. And if carbon dioxide increases, we know that E decreases. I'll show you the physics in this in a second. And this formula mathematically explains why, as carbon dioxide in the atmosphere increases, so our temperatures must increase as well. And there it is. And I said that's a good model. It's not a particularly sophisticated model. It's not a particularly, doesn't tell you too much, but it tells you one thing and it tells you that one thing well. I have pictures here of other things. So there's carbon dioxide coming out of chimneys, which will decrease E, but also methane coming out of cows will do the same thing as well. Yeah, slightly weird picture. Do you have permafrost in Canada?
Yes.
Yes. So as permafrost melts, that releases carbon dioxide, methane as well. So, and particularly permafrost in Siberia. Okay. Just to kind of show you how that works, again, the link between emissivity, E, and carbon dioxide, it's rock solid physics. The emissivity of the atmosphere depends upon carbon dioxide, methane, and water vapour, each combined. The bit due to carbon dioxide, that's the level of carbon dioxide as the level of carbon increases, so emissivity decreases. This is rock solid physics. Here's our carbon dioxide levels, nothing, whang. And so there we are. That gives us this issue that temperatures will increase. And I should say, I cheated. All the mathematicians in the audience should have shouted at me when I put this formula up, because actually this isn't really right. This is an equilibrium formula, and what really is happening is that there's a rate of change which is proportional to the difference. But basically, that rate of change allows things to kind of adjust, but this is going too fast for that rate of change to cut in. So, bang. And that kind of prediction is essentially what's going on in these very, very sophisticated models. So I've got some pictures here of current predictions of the rise in temperature, where people make various assumptions about the amount of carbon dioxide that's going to be shot into the atmosphere. And you get different answers depending on those assumptions. And they're kind of interesting. The top one at the top is CCSR, which is a climate centre in Japan. So they predict for a high rise. Now, Japan, of course, worries about high rises because they are an island nation. America, now this is US, I'm not quite sure, one of these probably is Canadian, I should check, sorry. Predict a lower increase in temperatures, that's NCAR. And I'm proud to say that the British supercomputer took this value and that one, added them together and divided by 2
Yeah.
to get the British.
There you go.
There you go.
How much energy is that?
Oh,
Yeah.
an enormous amount, yes. But they're all predicting things go up, and they say the variation is largely due to different assumptions on how much dioxide is. Things could actually change more rapidly than this. There's a thing called the albedo, ice albedo cycle, and it goes like this. The sea gets hotter, that's here. As the sea gets hotter, the ice melts, which we know. As the ice melts, less energy is reflected into the atmosphere, reflected in the sun. So because of that, the albedo decreases. As the albedo decreases, so according to our formula, the temperature rises. As the temperature rises, this melts, and round we go. And this is a feedback loop, and that's something we're watching. Okay? 'Cause, and there are other feedback loops. Another one would be the permafrost in Siberia. That gets hot, melts, methane released, temperature goes up, round and round we go. And the worry is if you get these things called tipping points, where you push things beyond a certain level, and when things go bang. I haven't got time to really go into the theory of that, but oops. I'll come to that in a second. Here are various tipping points identified where these sort of cycles can come in. This is due to a very good friend of mine called Tim Lenton, who is one of my collaborators in these climate centre things that I'm talking about. So there's the permafrost, there's the Arctic, Greenland, and one again that we worry about, particularly in the UK, is the Atlantic cycling and the effect of the global circulation in the Antarctic and everything else. So these are various things that can happen. So just to finish off, are we all doomed? I put this in because when I've given these talks in the past, people are unhappy. And of course not. I mean, the point about predictions, firstly, they may not be true. I think we're reasonably certain that they are true to a certain extent, but they give us some indication also what we should be doing. The Paris Accord basically says reduce your carbon dioxide, and that's sensible, and that is achieving. I mean, one of the things I'm particularly excited about is that the growth in renewables means that we are, in the UK, essentially burning no coal anymore. And a large amount of UK energy is now produced by wind energy. Again, I ought to know the figures for Canada, I apologise. But here's one of my take-home messages. We actually throw away an awful lot of energy, and we can actually, if even things like perhaps coffee, give away energy. Again, if I was giving this in the UK, I'd now take my Stirling engine out, because there are energy engines out there that can harvest all the energy that we throw away. And by doing so, we can actually use less energy by simply harvesting the energy that we throw away. So just to conclude, there's my lovely formula up there. Just that simple formula, to me, is worth any amount of political rhetoric, because that helps me understand why we get what we get. What should a mathematician do about climate change? Well, apart from all this kind of nonsense here, the most important thing I think we could do, and certainly we should be telling our students or whoever we're engaging with, is when you look at the climate debate, try to look at it through the idea of, how accurate are these models, how uncertain is the data, and so on, and use your mathematical judgment to kind of work out what's right and what's wrong. And if we all do that and take some of the kind of rhetoric out of the debate, more science in, I think we can all benefit. Thank you very much.
For some questions and comments.
Yes.
So you're talking about the methane being released by the melting of the permafrost.
Yes.
But how much thought has been given about the methane that's released by the, the production of gas, what's it called? Fracking.
Fracking. I simply don't know the answer to that. The methane stuff that I'm aware of that the IPCC looks like is, you know, the permafrost and also the use of animals like cows and stuff. Use a lot of methane. So that's a change in agricultural practice. No doubt fracking is producing other stuff as well. I simply don't know why.
Is that being done by the IPCC, or is that being investigated?
Probably, because they look at pretty well everything. Yes.
Are there any natural processes in the world or in the earth that capture carbon as it's emitted, or do these models take that into account, that what you're measuring is already...
Well, the classic thing which absorbs carbon dioxide are the rainforests. And those are very much more. So, it's vegetation is hugely
Do
important.
these models take that
The more
capture into
sophisticated models do very much take vegetation into account and the capturing of that and the changing the, if I whiz back to one of the graphics I had where I was get there yet. That's one. These are the models that they were using 10 years ago. So plants and soil very much built in that. The other thing is you've got chemistry in the atmosphere. So carbon dioxide also reacts up and that's taken into account. Again, if we sort of look at all of this, we have dynamic vegetation. One thing that people didn't realise until quite recently is the extreme importance of plankton in the thing. Another thing about carbon dioxide is, this is kind of worrying, is that the oceans absorb a lot of carbon dioxide. There's evidence that from prehistory, that the oceans can only absorb a certain amount and then they start releasing it. So we don't properly understand that process. Somehow it goes from the shallow down to the deep. So yes, there are all these processes and we put in as much as we can. Yes?
We were talking before about the mean going up, but also we were talking about the variance changing. Does the variance also increase?
It's a bit hard to say. Well, the variance doesn't need to increase for more extreme events to happen. So if we say variance of the amount of rainfall we get, that can increase markedly due to just a change in the mean of the temperature.
Yeah. I'm just wondering, like, if we know if the variance is...
There's no obvious reason to expect at the moment, but there's every reason to expect that the variance in the amount of rainfall will increase greatly, and therefore we'll see more extreme events. Yes?
Is that incorporate all of those different sub-models, or is there no...
Yes, the HADGEM model, HADGEM 4, which is the most recent model, has basically got all that in it.
So does it provide any additional information that the sub-models don't, like the interaction of two? Like,
Well, it's how they all interact is important. I mean, just to get them in the front. So the vegetation model accounts for how carbon dioxide will be absorbed in the forests as they change. The atmosphere model talks about what happens in the carbon dioxide. So it's how they all interact that matters. But this is why these things are hellishly complicated, but you try and test each of these individually to make them all work individually. Yeah.
I'm trying to think of the question. As the water levels rise, the sea levels rise, presumably the area of water on the Earth will increase as well. So that slide you showed is quite dramatic. What impact does that have on the reflection of energy? The more water
the main effect is the ice in terms of reflection. Water and land are kind of fairly similar in the way they reflect energy, so that doesn't change things too much.
Well, you may have answered my next question. The map, that same map, you show an awful lot of water flooding into Russia.
Yeah.
It's quite remarkable, actually. Does that cover the Siberian, like the tundra you're talking about in Russia? So this methane is now coming up through.
So that might change things. Yeah, that's a good point. Someone's probably taken that into account.
Oh, no, I'm just, as I saw it,
Yeah.
I'm thinking.
No, that's a good point. Thank you. I mean,
But it's not a good thing.
yeah. Yes.
You mentioned that there's a lot of uncertainty in these climate models. Is there something we can tell based on these uncertainties, like these data generated by us?
Well,
like,
sophisticated climate modelling estimates the uncertainty. So there's this branch of mathematics statistics called uncertainty quantification. And what that tries to do is say, well, we've got all this uncertainty due. There's three levels of uncertainty. There's uncertainty due to the data, there's uncertainty due to the model, and there's uncertainty due to the compute. And well, there's also uncertainty due to the way we initialize things as well. And it tries to kind of track all that uncertainty through, so that every prediction you make would have an associated uncertainty with it. And I haven't really covered that here because that's part of the more sophisticated models is to do that.
And then there's the uncertainty of the uncertainties.
Yes, yes. David back.
I'm just wondering if you can speak a bit about your approach to communicating with policymakers in terms of communicating that sort of complexity and the details, that overall sense of urgency.
That's a terrifically good question. I can only talk about the UK here. So the climate in the UK, the political climate in the UK is quite supportive. No, well, Brexit's bad, but anyway, essentially policymakers in the UK get it in terms of this. So when I talk to these climate networks that I'm involved with, we have policymakers are invited to come along and spend time with us and allows us to communicate. One of the great losses to the UK community was there was an amazing guy called David Mackay who wrote a book called Climate Change is a Load of Hot Air. I really, really recommend that you read this. And he was chief scientific advisor to the government on climate change. Incredibly good guy, proper scientist. His brother is a very good mathematician. But sadly, he died due to cancer a few years ago. But I really, really recommend that you have it's free. You just download it from the internet. Climate Change, a Load of Hot Air. Is it a Load of Hot Air? David Mackay. So essentially, they get it in the UK that there's an issue, and we communicate that way. I haven't tried doing it. I think Canada's a civilized country, so they probably get it. I can't speak for South Africa.
Maybe two more questions, then we go outside and you can.
Gentleman in the blue. Yes.
This is kind of a related question, right? So it seems like you're saying, okay, we take these simple models, right?
Yeah.
One with the albedo, the emissions. And it seems they're very simple.
Yeah.
And they tell you that the Earth is warm.
Yeah.
And that's great, right? Like, no one could really dispute that.
Yeah.
And then you move to these more complex models because you want detail, right? You want.
Well, you're looking at other effects as well.
Yeah, but I mean, like, you want to know, is this region or is that ocean?
Yeah.
Or is this city or whatever, like what it's going to look like?
But also you're looking at things like ocean current circulation and the effect of that, because that's vital and it's missed out from these things.
Right, but you're moving from like modeling the Earth as like a dot.
Yeah.
Like a sphere, right?
Yeah.
And so the thing is that when you do that, you're adding more variables.
Yes.
And more complex. And I'm assuming there's an associated uncertainty.
Yes. So as the models get more complicated, yes, they get less. They're less reliable in the sense that it's easier to make mistakes, and there's more uncertainty. So yeah.
Yeah. So I guess my question is like related to what you were saying. Like when you're talking to policymakers,
Yeah.
right? You'll tell them, look, we know the Earth is warm. They'll go, great. So what does it mean about for my constituents? You'll be like, oh, I don't know. Is there a bit of a challenge?
You
or
try to
contradiction?
give them. I think it's. I mean, going back to the lady's question, but personally, I think it's very important when talking to policymakers to be, as a scientist, as honest as you can.
Right.
To say these are the models we use. This is the uncertainty. to be honest, climate modelling is the most accurate thing they're going to have compared with these other models for the effect of climate on the ecosystem or on human behaviour. Okay. So you're giving them the best data and they've got to work with much more. So. And I just think it's an ethical issue for me to be fair on that. One more. You have to ask a question.
And this relates to policy, policy and how we organize our society, right?
Yeah.
So it's still an interesting scientific question, climate change, and it's very interesting. A lot to do, a lot of mathematics, a lot of. But I think it's especially important now to think about how we want to proceed in terms of how we organize our society. And this question, because of this, has become very important.
I mean, one of the things about climate models is that you can ask what-if questions. You can basically say, if we do this, this is what will happen. And you can do it without having to wait 20 years. So I think that's an important role that they have.
Okay, so I think let's thank Professor Dutt for their interesting talk. So there are some simple coffee and tea and some cookies, and you can still cook up.